You know, I think people when they do ensemble selection, they just do graded functional graded set using the validation set, and they just trust it.
They just work it out
Yeah.
well.
But it's technically like a second training set, like you're like learning in 2 steps. It's not really a validation set.
I'm sorry? I didn't catch that.
You're learning the second time, it's like not really validation set, you're like training just like on the second data with a reduced model complexity. Just
Yeah.
Like, you're like shrank down your model class, then the second model class.
That is true. You could think of ensemble selection as doing a linear combination over sort of a restricted set of models that you could possibly learn. If all these models are good models, linear combinations of them should not overfit too much, right? Yep, so the models are trained on S prime. And the ensemble, after the models are trained, the ensemble is built to optimize over V prime.
Could you explain once more how so H1 is one of the models among the 2000 which performs best on validation?
Yep, so H1 is the single best model that had the highest validation accuracy or lowest validation error. Yep.
No, but there is one such best, and then you pick that, and what is H2 then?
H2 is the single best model that when its predictions are added to H1's predictions, gives the greatest reduction in error on the validation set. And H3, again, it's a single best model such that when its predictions are added to the predictions of H1 plus H2, gives the single best reduction in error on the validation set.
If you also consider like a general linear combination of all those 2000 models and then decide the weights based on the validation set?
So there is a version of boosting that does what you're talking about, right? There is actually a version of boosting that does what you're talking about, and it actually works about as well as ensemble selection. But ensemble selection actually is attractive for reasons other than just it's attractive also because it's computationally more efficient. So typically ensemble selection is used over model classes that are very, very complicated, right? Because it doesn't care about the bias variance trade-off in its interpretation. It just says, I'm going to minimize the sum of the two, right? The validation. So
how many iterations do we do this? Because if we just keep doing it in the end, we are just adding up all the 2000 models.
well, yeah. So you can have repetition, right? Because like you can add the same model twice, right? Yeah. You can definitely have repetition. It's selection. You're selecting with replacement. Yeah.
You average out the predictions, or I mean, you're not training.
You add them.
Just add them, right?
You add them like this. Yeah.
But you're not training the second model on the residue from the first one, right? They're all training to predict the actual data as such. So if you just keep adding their predictions, you might.
I suppose you could average them. I guess it wouldn't matter. I mean, it doesn't really make a difference for classification, whether you average or add.
You're just taking a sign at the end.
Yeah.
Right?
Yeah. You're just taking a sign at the end. Yep.
So what was your answer to the question that was asked about overfitting on the validation set? Because to me, it seems like this is going to overfit to the validation set anyway.
It will overfit to the validation set, yes. Mm-hmm. The question, so if you really care about that a lot, what you would need to do is have another outer validation set. But that's problematic because now you're splitting your training data even less, and your models become less stable. Often people don't do that. And one intuition why that's okay is because all your models in H are good models, right? And you just learn the linear combination of good models.
Are there rules of thumb for how to split S? Like, is it 80-20, or is it just however?
You know, I actually don't know. I mean, I did know, I forget. I refer you to this paper for more details. It's a great paper. Yeah.
Why we just simply add models together? Why not put some weights in front of these models? for example, when you decide to add a model, you also consider, okay, there's a parameter to control how important this.
Yeah, it turns out not to help that much.
As soon as you have a replacement, you're basically doing that, right? Like I had the same model 10 times, I'd be like having 10 minutes away.
Yeah, it turns out that it just.
You need to average it.
Well, we just care about plus minus 1. So if it's above, you say if it's above 0.
Actually, it's only a prediction, so it doesn't matter, right?
Yeah.
Yeah, and in practice it doesn't help at all. So, expected test error is bias plus variance. Bagging focus on one side, boosting focus on the other side, ensemble selection. Who cares, right? I could be like my set of H, my 2,000 models, they could all be high bias, low variance, or vice versa. It doesn't matter. I'm agnostic, right? Just minimize the expected test error as measured by my validation set. Don't even worry about the bias variance. Yeah.
So if you know, like you have low bias models, for example, would you prefer bagging over Ensemble? Or?
If you knew for a fact that you had low bias models, yeah. Yeah, I think in practice what will often happen is bagging on ensemble selection will just give you the same result, close to the same answer, in which case bagging is certainly simpler to use. It's implemented, for example, already in scikit-learn, whereas bagging ensemble selection I don't think is implemented by default.
So what's the point of the first two?
What's that?
What's the point of having the first two if the third one sounds better?
What's the point of having the first
Like
two?
ensemble selection that would just be moderately better.
It can be computationally quite intensive. Like if one of those H is a boosted decision tree, one of those H was a bag decision tree, and you could have just used a bag decision tree, I mean, there is computational memory savings.
Do we also want to use cross validation when we use bagging or boosting?
Typically, bagging and boosting don't rely too much on cross-validation because they're the individual models. You may need to tune the hyperparameters of individual models with cross-validation, but you don't need to do so with bagging or boosting.
Okay, it's just a single process.
Yeah. It's not, ensemble selection is not a catch-all in the sense that the split on the validation can be problematic. Like bagging requires no split, right? And so there are cases where the H that you train using just the small training set is not as good as if you just did bagging and not bother with that. Yeah. So it's not unilaterally for free.
So if you have tons of computation, tons of data, then the ensemble would. So
If you have tons of computation, tons of data, methods like ensemble selection tend to dominate. Yeah. Yeah.
So it just seems like these get more and more complicated. People just keep adding more and more stuff. Is there a theory that says, what is the upper limit of the amount of information I can possibly capture in a data set anyway?
That is a very profound and abstract
So-
question.
So, let's say you measure something, right? People's preferences, and here you are. You know
Yeah.
nothing about the process. You're just you know nothing about the data.
Yeah.
But you know that there's some noise in the data. So obviously you can't capture all the information. There's a
Yeah.
limit to how much information is represented.
Sure.
Kind of like a Carnot cycle for machine learning.
Uh-huh.
Is there any theory that says you can keep adding as many models as you want, but you reach the total amount of information you can possibly capture?
In order for any theory like that to be provable, you need to make a lot of assumptions. Right? You need to make assumptions about the process that generated the data.
That's right.
And so, yeah, people have theories like that, but those assumptions are interesting to think about, but all of them are just simplifications of the real world. So people do study this, and yes, you can definitely get that. In general, it was basically more data never hurts because it reduces the uncertainty caused by the noise more, and more data never hurts. You might ask, what is the law of diminishing returns and collecting more data, people looked at convergence curves, like if the error, with this data the error is this data. So like, you know, how quickly does the variance of your model class decrease as you use the same model class but in more training data, right? And that curve typically goes like this and it flattens out, right? And you could ask the question, you know, if each data point costs this much money, at what point is it not cost effective, right? And each point, if each data point costs this much money, and each unit of variance reduction is worth this much money, what's the break-even point? You could ask those types of questions, right? But the more data never hurts. It'll always help, if ever so slightly.
Well, but there are like entry bounds on like unbiased, like minimum variance estimators and things like that. Or tell you something about like how well you can possibly do on an estimator or something.
Yeah, but you'll asymptotically approach that as you.
Yeah, but that tells you you can like drive stuff. It might be a really bad bound, but there are, you know, statistical like.
Right, but you'll never actually approach that with a finite training set.
Yeah.
In the case where you have noise in your measurements, and as you get infinite training data, you will approach that in the limit, but you never actually reach it exactly with finite training data. Yeah. Sorry, let's take this question. Yeah.
Yeah, just to address against this validation and overfitting thing, so.
Really concerned about the Kaggle competition, I see.
I was thinking, is it okay that we're not overfitting on the validation set because the expressiveness of our second model class is so low that we can basically generalize and we can get away with it?
So that's the intuition that, like, you know, no linear combination of the predictions, because the ensemble model class is basically the linear combinations of the predictions of your base classifiers, right?
Well, not even linear combination, just like, I mean, even smaller because we don't have coefficients. I'm just wondering if the idea of that is that, like, we're doing that, but we can afford to not have validation because the expressiveness of the model is so small?
No, I don't think that's it.
No, because otherwise I was thinking.
And that's just for computational memory convenience, yeah.
So it's good to happen that we have so many models that we then overfit and then we overfit the validation. If we have too much models, so we have to like watch out that we have only a few models. Is that?
Yeah, if your ensemble methods are.
If you have like 1 million of them and they're like basically can capture everything, and I can see that when you train them on the validation set, you would definitely overfit everything.
Yeah, I mean, it's certainly the case that the theory of ensemble selection is non-existent. But let me think. In practice, people use ensemble selection with already good models. I think no one uses like weak models in ensemble selection. They're already like good models, like a boosted decision tree, a back decision tree, an SVM, a neural map. So this is just an example of a result from this paper, where just according to a bunch of different metrics, ensemble selection does the best. And in this particular experiment, the base models within the ensemble selection were 2,000 models outperform a boosted decision tree, a bagged decision tree, a random forest, and so on and so forth. Okay, if you're interested in references, here's a bunch. All right. So next week we'll be talking about probabilistic models and Markov models and looking at recitation time.